Okay, so today we are gonna start chapter 4. Okay, as I told you before, I can divide this course into two parts. In the first part, and that's what we finished, is actually about the basics. Okay, so here I can say chapters 1 to 3. These are like the basics of logic gates and circuits. Okay, and we have finished this one. The second part is actually I'm going to teach how can we use the knowledge we learned in chapter 1 to 3 in order to create some basic logic circuits. Okay, and these logic circuits or the basic logic circuits in other courses in the future, you will learn how can we create a computer or how can we create a system using these basic logic circuits. Okay. For example, here in this chapter, I'm going to talk about something like other converter, subtractor. So how can we make a hardware circuit to do addition or subtraction? This is one of the component of any computer or any digital system. Multiplier, comparator, also decoders, multiplexers. So these are also basic components. In the future, I'm going to also talk about registers, counters, and other things as well. All of these are just basic components. We use them to create a digital system. Okay, so and here actually these logic circuits here we can actually divide it also into two parts. The first part that would gonna be in chapter 4, and that's what we call combinational logic. Okay, there is another type of logic we call it. I think I mix the difference here. So here we have combinational circuits and also sequential circuits. Well, I can divide them into two types. Okay, in this chapter I'm going to talk about combinational circuits. In the coming chapters I'm going to talk about sequential circuits. Okay, the main difference between them is, okay, here in the sequential circuit we are going to have some memory elements. Also we're going to have some feedback. When I say feedback, you know what feedback means. You get from the output, you put it in the input. Okay. In other words, let it make it, you are not going to understand what I'm saying here until I do it in next chapter. But for now, I can make a very small definition to understand the difference between these two. But in this chapter, we're going to focus on combinational, and everything we did so far is actually combinational as well. Okay. So in combinational, I can say the output I'm going to get from the circuit depends only on the input you put here, only on the input. Okay. However, in sequential, the output here depends on the input and also the previous output, the last state. So we're going to talk about this one later, but let's focus on this chapter. So here, what we have learned from the previous chapter, any logic circuit, that's what we did so far. It can have n inputs, also it can have m outputs. Okay, you apply here binary, and then you have here some gates, and this gate has to produce binary here at the output. Okay, however, all what we have done so far, we have only one output here, not m, only one. Okay, but I made it clear in several lectures. I told you also all the examples we had, well, it was only one output, but actually it can be more than one output, and that's what you are going to see in this chapter anyway. Okay, so let me read what I wrote here. If you have a circuit and this circuit has an input variable, so how many possible combination we have? How many interests, how many rows we are going to have in the truth table? Should be 2 to the power n. This is all the case. That's what we have done. Okay, and then this is the input, and then we have only one possible output. Okay, one either it's one value or multiple value. So for every input, we have only one output. Make sense? That's why that's actually what we did. That is why we can use a truth table in order to make the relation between the input and output. And that's what we did. What we did before, we had a truth table. When this is the input, the output should be 1, or the output should be 0, okay? And so on. So using this truth table, I can actually design the circuit. So here, nothing is new here, because actually this chapter is not different from what we did before. The only difference is what we did before, it was learning how can you do simplification, how can you do all this stuff. So I just put ones and zeros randomly. Somehow, so the circuits themselves don't do a specific thing, but this will be different in this chapter. Okay. So here, I'm going to explain, if you want to design a circuit, what you have to do. Again, nothing here is new, but because what I'm going to explain here is similar to what we did before. Okay. Number one, from the specification, I want to do circuit to do something. So I have to give you a specification. I have to tell you what this circuit has to do. Okay. So from the specification I give to you for the circuit, you have to determine how many inputs I need and how many outputs are needed. And then you have to assign symbols for them. This is step number one. So step number one, if I give you a problem and I tell you I want to design a logic circuit to do something, I'm going to give you specification. From this specification, you have to decide how many inputs you need, how many outputs you need, and then assign symbols for them. Number two, you need to create a truth table. This truth table should have the relation between the input and the output. Okay, so and that's actually what I'm going to do in this lab, in this week lab. Okay, in lab number 6. In lab number 6, for Fibonacci number. Okay, so I give you specifications. You have here, you have 3 variables here, and for every case, you have to say is that Fibonacci put 1, not Fibonacci put 0, and so on. Okay, and then after that, what we did before, we need to simplify the function. We need from the truth table. So now I'm going to design the truth table so that this circuit has to do something. Okay, and what the circuit has to do should be specified. And then after that, you need to do simplification as you did before. After you do simplification, you can draw the logic circuit. On top of that, you can also do verification or validation. Okay, how can you do validation? Can anybody tell me if I really simplify the function and I want to make sure this function is correct, how I can do that? How I test it? Huh? Yeah, simulation can be one thing, but if you want to do it by yourself, how can you do it? So I got a function, I give you a function, you simplified it, and I got simplified one. I want to check if this simplified one is correct or not. What should I do? This is a question in today's quiz, by the way. Okay, but anyway, what should I do? Yes, that's true. So what you have to do is you have to calculate the truth table for the simplified one, and if the truth table is equivalent to the original one, that means it's true. You got what I'm saying? Anyway, so after you get the function, after you simplify it, you can do some kind of correction. Anyway, this is the basic way, or this is the basic steps we have to do if you want to design any function or any circuit. However, as you will see today, sometimes I'm not going to follow this one. I'm going to tell you why. Sometimes I have too many inputs. Remember, we have here we have a big problem here. I'm going to tell you what is the big problem. Think about it. If you have 2 to the power of 2, so how many cases? We assume we have 2 variables. Okay, so we assume you have 2 inputs. So how many cases you have in the truth table? It should be 2 to the power of 2, which is 4. Okay, now if I add only one variable, if I increase it by only one variable, what's going to happen? It's going to be 2 to the power 2, which is 3, sorry, which is equal to 8. That means the truth table is going to be double. This is a very, very bad issue. I'm going to tell you why. Okay, this is because imagine, for example, if I have, for example, 5 inputs, that means our 8 inputs, if I go for example, to 8 inputs, so we're going to have 256. And if you have 10 inputs, we're going to go for 1012. Sorry, 24, 1024. You got what I'm saying? So that means what I want to say is the problem is every time you increase the input by one variable, the truth table is going to double. Okay, so imagine if you have 10 inputs, the truth table you are going to have 1024 rows. For sure, that's going to be very difficult to design a circuit like this. So what I want to say, all the time you are going to follow something like that, these steps, and that's what we have done so far. But keep in mind, this is not going to be realistic. It's not going to be realistic when you have too many inputs. And too many inputs here, I don't mean 100 or 200 inputs. I mean even just 10 is too many, because this is 2 to the power of something. It's exponential, so bad. Okay, that's how it is. Anyway, so we need to find other way, and that's what I'm going to teach in today's lecture, hopefully. So now, so what I'm going to do in this chapter, I'm going to show you how can we do converters and what is converters and why you need them. Also, I'm going to talk about other subtractor, how I can do multiplier. So I want to do a circuit that can do multiplication, comparator, and so on. So I'm going to show you one by one. So let's start with the first one, converter. So as I explained in chapter 1, in binary, we have different types of codes. For example, BCD is a code. And we have another code, we call it, for example, access 3. This is a different code, okay? So what if you have a circuit and this circuit is using BCD code, and then I have another circuit, okay, that's using the code access3 code, for example, and I want to connect the output here to the input here. Can I do it directly? For sure, no, you can't, because they are using different language. They need a translator in the middle. You get what I'm saying? Because the code here is different from the code here. That's why you put here a circuit. This circuit has to take BCD code and it has to convert it to access3 code. And that's what I'm gonna do today. So I'm gonna show you how can you design a converter or a logic circuit that takes BCD and convert it to access3 code. Okay, and it can be useful in a case like this one. Okay, any questions? So let me tell you what is BCD. You already know what is BCD, what's access3. So in here, what I'm gonna do here, because this is just a very simple circuit. So I'm gonna follow these steps, and again, these steps are not different from what we have done so far in this course. Okay, so let's start here. So as you know, in case of BCD, how many numbers we have in BCD? You know, in BCD we have numbers from 0 to 9, and to represent this number, we represent every digit, okay, as binary in 4 bits, because we need 4 bits. It can't be 3, because if the 3 is going to be limited to 7. But BCD we have 9. Okay, so what we have here, I need here. This is the input of the circuit. This is the input of the converter. So the converter, the input of it is BCD. The output is going to be the code for access3. So I'm going to talk about it. Okay, so here what should happen, if you have this input in BCD, I'm gonna get the equivalent to code in access3. Same thing for every code here. I'm gonna get the equivalent one in access3 code. So here, as you know, we have here numbers from 0 until 9. However, because these 4 bits, you can have numbers until 15. Okay, but these numbers, I'm not gonna use them. They shouldn't happen. That's why these ones will become don't care. Okay, that's what I'm gonna do. I'm not putting here in the truth table, but because they will be don't care. It's not a part of the input anyway. Okay, so let's talk about access3. You can tell from the English name access3. Access3 means you add 3. Okay, because that's how it works. This is how the code is. So how the way this code works is, if here in case of number 0, you will see here it's going to be 3. Okay, in case of number 1, it becomes 4, and so on. in case last one here, number 9 is going to be 13. Is that right? Oh, sorry, you add 3, it should be 12. Is that okay? So here, that means in this system, this means 0. Okay, if I use this circuit or if I use this code, this one here means number 2. So number 2 here means this one. Okay? So we always add 3 in this code. Okay. The one someone can ask me, so why sometimes we need a code like this one? Just okay. So again, what I did here, I don't, just to make it very simple, guys, it's just different. It's like representation to the number. So this is a representation of 0. Here, this is a representation of 0 in this code, and so on. This is a representation of number 9. This is a representation for number 9 here. Just a different representation. But if you can do some search, you can see why some people may find this one is more interesting than using the PCD to represent the numbers this way. Why this one is more interesting. We're not going to use it in this course, okay? But here I put 2 reasons. I put 2 reasons here. I didn't use it, so I did a quick search. So here, the first thing here is number 1. They are saying if there is access 3 is not using this pattern, it's not using 0, 0, 0 or 1, 1, 1, 1. And this is good because if there is a fault, if there is a fault in memory or basic transmission, usually this fault is going to result in these 2. So you get what I'm saying? So I'm not going to get confused. If there is a fault, you are going to get 0, 0, 0. If you use BCD, I will be confused because I will take it as a valid number. But here in this case, another thing here, sometimes, especially if you want to write to magnetic media, sometimes it's more difficult to write 0 than writing ones. That's why I need more ones in the code than zeros. You know what I'm saying? And this is very obvious here because every time we add 3, if you look here, we have here more ones than the ones we have here. Anyway, I'm not gonna go into this. I just want to focus on the circuit and the design. But what you should understand here is we have PCD code and also we have XS3 code. Some logic circuits use this one, some logic circuits use this one. Okay, and now I'm gonna focus on I didn't receive anything. It looks like my phone is too old. This is test, right? National test, right? Okay. Anyway, so here, so now, as I told you, if we have a system, okay, so I told you now, if I have systems that using this code and I have another system using this code and I want to connect these systems together, I need a converter. And here I'm it's too late. Okay, so we need a converter here to convert from one code to another. So this code actually to be more, so here the code I'm gonna teach now is gonna convert BCD to XS3. You can redesign the circuit to do the opposite. So this circuit doesn't do the opposite, okay? You can redesign. Anyway, so let's focus on, so now, if you think this way, this is the truth table I have. So I have 4 inputs and I have 4 outputs. So now I have a circuit. This circuit has 4 inputs. I'm gonna call them A, B, C, D. And it should have 4 outputs. I'm gonna call them X, Y, W, X, Y, Z. Is that okay? And now I wanna design the circuit here so that for each input here, I'm gonna get this output here. Is that okay? Okay. How can we do that? This is again, this is similar to what we did before exactly, but the only difference what we did before, we only used to have only one output. Is that okay? Now we have multiple outputs. It's gonna be the same thing as you will see right now. So what I'm gonna do, I'm gonna take this output, I'm gonna design a circuit. Okay, similar to what we did before, right? Same thing. And then I'm gonna take this one as the output and design the circuit and so on. So that's what I'm gonna do. So what I'm gonna do here, as you see here, I have a figure this way. So you can imagine as if we have a function for this one. This is like one output, like what we did before, and you can get a function. So here it's something. So it means you can say I'm gonna make here, I'm gonna make 4 circuits. 4 circuits. One circuit, this circuit is gonna take the output A, B, C, D, and then it's gonna output W only W. Second one is gonna take A, B, C, D, and then it's gonna output X, and so on. Like we have 4 of them. So when I design, I'm gonna design everyone individually. You understand what I'm saying, guys? So this is similar to what we did before, but what we did before, it was only one. So this time, I'm gonna take one. I'm gonna consider this is the output, design the circuit using key maps. So how many key maps I need here? 4. So I need key map to design this one. Key map here, key map here, key map here. Similar to what we did. Nothing. Okay. So as you see here, for I'm not gonna go in much details, but as you see here, I'm gonna make a key map for this one to design W. So here, this is, I think, I'm gonna make one by one. For example, if I start with Z, this is Z, okay? Z is this one here, this one is Z. So similar to what we did before, we have don't care this way. And then I have once here, okay? And then after that, I have to do simplification as we did before. So if I do simplification, this one here and this one here, I will find Z is equal D prime. That's it. So if you want to get, in other words, if I get this D and I invert this one, I'm going to get this truth table here. I'm going to get this truth table. Is that okay? That's it. So here, this one is going to be too simple. Z, so Z is equal just D prime. That's it. Okay. After I did the simplification. Now, let's look, for example, how can we do Y? For example, same thing as we did before. Y. So I'm gonna work on Y here. Okay. By the way, I just randomly started from right to left, but it doesn't matter if right to left or left to right. It doesn't matter. You get what I'm saying? Okay, I don't because these small things make me confuse some students. Okay, so after I finish this one, so now I'm gonna go for W. Okay, so here for W, as you see here, we have once here in this location, we have once here. So if I come here and go for W here, yeah, I put the ones here. Okay, so this is circuit for W, and then after that, as we did before, you can have you have 3 groups. So this one can be one group. Thanks to don't care, it can be very simplified, and then another group here, and then another group here. If you do this way, so from the input, I can get W using this logic expression. Is that okay? Any questions? Okay. Same thing for the other two. For the other two, I can do the same thing. And now the conclusion is now. Okay, so now I have this circuit. I have another circuit, or another circuit. So now all what I can do, the very simple way to do it is, okay, so this is here. I'm gonna make here the first circuit here, and then I'm gonna input for each one of them as I'm explained here. So for every one of them, I'm gonna input A, B, C, D for each one of them. For sure, here you don't need Z. So I don't need to sorry, here this one is only D prime. This one is only D prime, so it doesn't need ABC. Okay, so to do this one, it is just inverter from D. So this one needs only D, right? Anyway, same thing for the other ones here. So again, what I did here similar to exactly same thing like what I did before, but what I did before, the output was only one. Now we have 4 outputs. Okay, so which is similar. It's like 4 problems. So for every output separately, you have to make a key map and you have to simplify separately. Any questions? Okay, I'm gonna tell you another something somehow interesting. So now I got 1, 2, 3, 4. I got 4 expressions or 4 functions. Is that okay? I can implement them separately, I am sure this is a most simplified function. This is a most simplified function. This is a most simplified function. This one is the most simplified function. Is that okay? However, if I use all of them, when I implement, now in implementation, when I implement all of them, okay, can I do a second layer of simplification? What do you mean? I mean, if something is common here and here, okay, or if something I can make it common between here and here, in this case, I can make only one gate, and this gate is going to serve here and here. So this is like a second layer of simplification. That in the first one, I just focused on every function alone. Now, if I do everything together, is that okay? The worst case is, or the most unsimplified one is, just do everyone's individually, and that's okay. However, you can also, as I'm going to teach right now, you can also, when I implement all of them together, also I can do some tricks to simplify, as you will see right now, okay? So, but this one has to be done by algebra manipulation, okay? So that's what I'm going to show right now. So what I'm going to show right now is, look what I did here. Just to do, it's like a second layer of simplification. So what I did here is, this is the output I got from the key map. So the key map gives me this one. However, I'm going to do a simple thing, as you see here. I'm going to use De Morgan here to make this one this way. I'm going to tell you why, okay? Same thing for X. That's what I get. That's what key map gives me for X. Now also I'm going to do here, because P prime is common between this one and remember, I'm not doing simplification because everyone is the most simplified one. I can't simplify it more. You understand what I'm saying? So everyone individually is the most simplified one. So I'm trying to find some common terms, so that this common terms, I can make one circuit, and out of this circuit, it's gonna go to several ones. You understand what I'm saying? So it's like rearrangement. It's not gonna. It's rearrangement for everyone, because everyone is the most simplified one. Okay? That's what I want to say. So here, so I just rearrange this one so that I can have this term C or D. Okay. Same thing here also. I noticed here, if I take P prime common, I'm gonna have C or D. So it looks like I have a common term here between all of them. Okay. And this one here. Again, and also what I did. So here, what I did here in this one is, yeah. So I did also here a simple, yeah. So what I did here, if you see what I did here for this one, so this one is actually equivalent to B, okay? And C prime D prime is actually C or D all prime. Is that right? That's right, okay? So okay, so just I did some modification. Okay, so instead of using the one I got from KeyMap, I did little bit more. And because of this modification, I can see some common terms here. And this common terms is gonna make it, it's like a second layer of simplification. But anyway, so what is the common part here? The common part is, you can see here, C or B prime. C or B prime. Okay, so I can implement it once, and the output go here and go there. Got what I'm saying? Also here we have C or D and C or D. So this part is common as well. Okay, and that's exactly what I did. So in order to, let's now implement this circuit. So again, this is the input here, A, B, C, D, and this is the output here, W, okay? And this is the converter. So this is how I can do conversion. So let's start one by one. So first of all, if you look at Z is just a D prime. That's it, okay? And that's what I did here. If I look at this part here, how I did it, so Z is actually D prime. Is that okay? Now, if you look at Y, I can implement it this way, or as I told you, I'm gonna do this way just for more simplification. Okay. So if you look at Y, actually we have or this or between CD. So CD is gonna come here, and C and D, and also we have here C or D, and we have here C or D prime. And this is the main thing. Look here, guys. Because this term is common, C or D here, I need it C or D. I need it here and I need it here. So I can only implement one circuit, and C or D is gonna come here and also come here. Okay. And now we have C or D prime. I just put one inverter here. So now I have, this is the common part. These two are common, okay? Because we have here C or D prime and C or T prime. So I'm gonna input this one here. Also, I'm gonna input this one. Is that okay? Okay. So if you look here, again, for Y, this is what I got from KMap from Y. I did little bit modification to be this way. And exactly that's what I did here. So you have here CD and you have C or D prime here. Okay, so I got Y. Same thing for the other things. For example, if you look at W, I have OR, here this is W. So one input here should be A. The other input, the second input should be between B and C or D, right? So it's gonna be exactly the same thing like this one, okay? This one here is gonna be OR between two things, OR A. This one is OR between two things. The first thing is B prime and C or D. Yeah, so if you see here, this is B, C or D prime, which is this part here. But if you look at this one, B prime, okay, and this one is C or D, C or D. So this one is gonna give you the second term. Okay, guys, any questions? Understand what I did? So number one, conclusion, before I move forward. The conclusion is, again, nothing is new until now. This is similar to everything we did before. The only difference is what we had before, it was only one output. Or we always have one output, but here the output was only 1 bit, right? Here the output is actually 4 bits. Okay, that's what I want to see. The output is 4 bits. So here, so now it's gonna become like you have 4 problems. So I'm gonna work on this one alone to do simplification for this one. I'm gonna work on this one alone to do the simplification. That's why we have four key maps. So I'm gonna consider every bit like a separate function, okay? And then get the most simplified one. And then what I did here, and after I am done, I can do another layer of simplification in the way I can integrate these ones together. Okay, I'm gonna repeat it again because this is so serious. Okay, what I'm saying is I didn't do another simplification for the functions I got because using key maps are gonna give me the most simplified ones. I just did simplification in the way I'm gonna integrate them together. Okay, if I find something common between them, I can, instead of doing 2 logic, I can just do 1, and because it's too common, I can put in both of them. So I didn't do simplification for this one, okay, because this is the most simplified one. I did simplification between them, among them. Okay, if something is common, I can implement it only once. And to do that, it's gonna be Boolean algebra. Okay? Any questions? Good. So now let's go to other and subtractor. So you can tell from the English name, I want to design a hardware circuit. This hardware circuit should get numbers, binary number, and it should do addition or subtraction. So I'm going to explain how can we do it. We're going to start with the simple case. The simple case, if you want to add 1 bit to 1 bit. So I have here 1 bit, okay, X and Y. This is 1 bit, and I want to add it to another bit to bit. Is that okay? So if I want to add X to Y, the result should be S and also carry, right? So if you add 1 bit to 1 bit, the result is 1 bit and the carry. Okay, is that right? So that's exactly what I want to do. So here I want to do a very simple circuit. This circuit should have 1 bit and 1 bit. I want to add these 2 bits together and I get some and I get carry. Is that okay? What should be the circuit here? What logic I have to use here so that this circuit should do addition 1 bit to 1 bit? Okay. Any questions? So again, similar, exactly same thing as I did before. If you think about it, so now we have two bits input and we have 2 bits at the output here. Is that okay? This is the output 2 and this is 2. Okay. Now let's make the truth table. Let's make the truth table. For the input, that's easy. This is similar to what we did before. You have to put all possible cases here. 0, 1, 0, 1, similar to what we did. Now, you need to fill this one up. That's what you have to do. So let's do it, okay? If you add 0 plus 0, what is the result? 0. And what is the carry? No carry. That's okay. Now, if I add 0 plus 1, the result is 1. No carry. Now, if I add 1 to 0, the result is 1 and no carry. Now, I want to add 1 to 1. The result is 0, right? And we have a carry. Okay. So now I created the truth table to do the functionality of addition. And now I want to create the logic circuit that can do this truth table. Is that okay? So similar to what we have done before, you are going to take this one as a function. You are going to take this one also as a function, and you can do the simplification. And because this is only 2 variables, simplification should be very easy. You don't need maths. It's only 2 variables. You don't need maths. You can even do it by algebra. Anyway, so after doing the simplification, we found that, or we can actually we can do it now here. So look here at C, for example. This is the only case here it has to give you 1. So in order to do it this way, just simple, it's simple end. That's it. And X and Y. That's it. In order to get only 1 when the 2 inputs are 1 and 0 everywhere else. That's why here the carry is just simple end between X and Y. Is that okay? Let's look at the other case. Other case here. Here, I'm gonna get ones here. Okay, I'm gonna get ones here. If the 2 inputs are zeros, I have to get 0. If the 2 inputs are 1, I have to get 0. When the 2 inputs are different, I have to get 1. Do you remember we did something like that before? When they are different, you get 1. When they are the same, you get 0. You remember we did something like that before? XOR. That's true. So the XOR. So here, if I do just XOR between X and Y, I'm gonna get S summation. And XOR, this is the formula for XOR. XY prime or X prime 1. This is XOR. Yes, I can do it. XOR is gonna give you 1. Example is different. Okay, so that means if I wanna do this simple, for sure, this is just very simple, but I'm gonna build on it. I'm making something simple, and now I'm gonna move up. I'm gonna build on it. Just here we are adding bit to bit. So the conclusion is this circuit has to be inside here. Okay. Okay, I will take your question very soon. So here, if you want to implement it this way, yeah. So here, this is this one here. You can get some and you get C, or as you have just said right now, I can use XOR. By the way, this is XOR. Don't be confused. So this is also XOR. XY prime or X prime Y. So this part here is equivalent to XOR. Okay. XOR is very useful. I didn't teach you before. I just explained before what is XOR, but I didn't tell you how we are going to use it because it's coming here. Yes, your question. It's coming. It's coming. Now I start only with I want to add 1 bit to 1 bit. Okay.
I was just going to ask if it works.
It's going to work what?
I was going to ask
if you want to add 3 bits together, or if you want to add 2 bit, 2 bit, 2 bit, or what you want to do exactly.
Like each bit had a logic high signals. 1 plus 1 plus 1 is 3. So
No, wait a second. You have to tell me exactly. You want to add 2 numbers, and the first number is more than 1 bit, because now I'm adding 2 numbers, but every number is 1 bit. What I'm going to explain after that, how can you add 2 numbers, and for example, every number can be 2 bits or 3 bits, or you want to do something else, you want to add more than 2 numbers. So the other here in this section, the other or subtraction I'm going to talk about is going to work only on 2 numbers, okay? Because for example, if I want to add 3 numbers, A plus B plus C, for example, I can do this addition first, and then I can do this addition second. So always we need to add 2 numbers, okay? Or if you want to add them at the same time, you can, but you need to design a new circuit. But here we are going to focus on adding 2 numbers. in the very beginning here, I explained if you want to add two numbers, okay, and every number here is only one bit. That's what I explained. Is that okay? Any questions? Okay, what I want to explain right now, what if your number is 2 bits? How can you do it if it is 2 bits? I'm going to tell you how. If it is 2 bits, for example, as you see here, we have 2 bits and 2 bits. Okay, so how many inputs you are going to have now? I'm going to have, if it is 2 bits, if you have 2 bits, so that means I should have 2 to the power of 4, 2n, right? 2n. N is how many bits you add to how many bits. So if it is 2 bit, so 2 and 2. Okay, so so this is one number and this is the other number. So it's going to be 2 to the power of 4, which is 16. Is that right? So, and you can make a truth table like that, and you do the same thing as I did before. You can do that. For example, as you see here, if I want to add this number to this number, 0, 0, I add it to 0, 0. What is the result? The result should be 0, 0. Okay, and there is no carry. It should be this way. Okay, same thing. I can do the same thing here. So every time, if I want to add this 2 number to this number, I have to get this result. If I want to add this number to this number, 1, 1 to 1, 1. 1 plus 1 is 0, and we have 1 here. 3 ones 1, and then we have 1 here. So I have to get this one. You can do this way. Is that okay? And then you have to build a circuit based on that, as I have just did right now. Is that okay? Now we're gonna have a very serious problem. What is the problem? The problem is, what if I want to make other, as I just told you, 4 bit other, 4 bit. So I want to add 4 bit to 4 bit. How many inputs you have? 8 inputs, okay? Because 4 and 4. In this case, I need 256 interest in the queue, right? Same thing. What if your other is 5 bits? You need 1,000 or something, right? That is why it's not going to be efficient to do this way. We need to think about another way. Okay, guys? So again, what I have explained so far in this course is, if you want to design a circuit, you have to go to the truth table. Simplify the truth table, get the function. Is that okay? However, it's not going to work all the time, or it's not going to be the best way if you have too many inputs. And this is going to be and this is the case in case of other, because number of input I have to multiply it by 2 because I have 2 numbers. So if I add 8 bits to 8 bits, so now I have 16 inputs. You got what I'm saying? That is why we're not gonna, for sure, if you want to do this way, that's okay. But usually, because it's not for 2 bit number may be okay, but I'm talking about if you have 4 bit or 5 bits or more than that, it's a truth table is going to be too big, and we need to find a smarter way to do it. Is that okay? Okay. You know what we're going to do? What do you mean by the smarter way? I'm going to tell you what I mean by the smarter way. Look here, guys. If you have, for example, 4 bit, you want to add 4 bit to 4 bit. For example, I have number A and number B. Listen to me. For A, we have here A0, A1, A2, A3. So these are the individual bits. For number B, we have B0, we have B1, we have B2, we have B3. Is that okay? So what should I do? I have to add these 2 numbers together. Is that okay? And then if there is a carry, I have to move it here and do the addition here. Same thing here. I need to add here 3 bits. If there is a carry, it has to come here. I have to add 3 bits here. If there is a carry, it has to come here and add 3 bits here. That's what we have to do, right? So in the first one here, I want to add 1 bit to 1 bit. That's it. And give me result and give me carry. And the carry, I can use it here. Make sense? Do you have a circuit that can add 3 bits? No, but I can make it. Okay. So all what I need to implement this idea. All what I need, I need 1 circuit to add 2 bits. I call it half other. And then I'm gonna make another one. I'm gonna call it full other. So the full other actually is gonna add 3 bits and it's gonna give me summation and carry. This one also gives me summation and carry, but it's gonna add only 2 bits. Again, why you are gonna make this full other? Simply because to add these 2 together, I have to consider the carry that's gonna come. So if really, I have to add 3 bits here. You got what I'm saying? So here I can use half other here, okay? And since a carry resulted from here, I can bring it here, and then I use here full other. You understand what I'm saying? Any questions? By this way, okay, all what I have to do, just design half other, design full other, and that's it. And by this way, if you want to add 1,000 bits to 1,000 bits, just 1,000 one half other, and 999 or 999 half full other, and that's it. It's going to be much easier to implement than making a truth table that has more than 1,000 entries. You understand what I'm saying? Any question? Okay, so let me tell you the conclusion before. Yeah, so conclusion is, I'm going to jump a little bit. Yeah, so this is the conclusion. The conclusion is, if I want to add these two numbers, E0, E1, 2, 3, B0, B1, B2, 3, if I want to add this one, as I told you, in the first one here, in the first one, there is no carry in the input for sure. Here I put a carry for a reason, but forget it for now. So there is no carry for the first one for sure. So all what I need here in the very beginning, I need half other. So all what I need here, I need only half other here. Okay. So here I'm gonna take the first bits, input to half other. Half other is gonna give me result. It's gonna give me a carry. This carry has to be added. So here I have to use full other, because full other is going to be used to add 3 bits. 2 bits, A1, B1, and C1. Okay? Same thing to next one, same thing to next one, same, and that's it. Easy way to make a parallel, we call it parallel, but 4-bit parallel other. Very easy way. Okay? And if you wanna make it 5-bit, very simple. Just add one full other. If you want to make 7-bit, just every time you want to add 1 bit, just add one other. That's it, full other. You got what I'm saying? For sure, there is, yeah, this one is much simpler than creating a very long table, but it has some problem we are going to talk about. Okay. Someone actually, so, but usually, by the way, so although here in the beginning, it is enough to have half other here in the beginning. It's enough to have half other, but usually we put here full other, and we assume we have a carry coming here. If there is no carry, you can just put 0. But why? So here I can just put 0 here. Okay, I'm gonna tell you why. Because when you buy a chip, if there is some chips that can do that. If you buy a chip, this is a chip that can do other here. Okay, so this chip should have E0, B0, E1, B1, E2, B2. So these are for the 2 numbers. Okay, and it has to give me the 4-bit result and have to give you a carry. And also we have input carry here, input. So the input carry is the carry that's gonna come here. Okay. So why you make it this way? I don't need it. I'm gonna make it 0. Okay, make it 0. No problem. You can make it 0. No problem. However, if I get this chip and it's 4-bit, and I get another chip that's 4-bit, yes, I can take C4 here. I input it here as C0. You get what I'm saying? So if I want to add 8 bits in the first 4 bits, I'm gonna put 0 for sure. I have to put 0. There's nothing. However, this one can be compatible. I can just add chips here. So if I have another chip here, okay, another 4. So here I'm gonna take C4, which is the output of this one, the carry output from here. I'm gonna input here as a C0. Okay. Any questions? Okay. So now I want you to understand why I changed the way we usually design circuit. Okay, that's because the truth table is going to be too long. I need a more efficient way. Just you can cascade in here. Okay, that's what you should understand why I did that. Number 2, you should understand how this one works. And in order to make it work, I need to design what we call full other. I have already designed half other. Half other can add 1 bit to 1 bit. Now I'm going to show you, we need to design a full other. Full other should add 3 bits together, as you see here. 1, 2, 3 bits together. It has to produce a carry, and sum. Okay. And to do that, I'm going to use the truth table because that's a small one. Small one, you can use the truth table as we did before. That's what I'm going to do now. So what I'm gonna do now is, as you see here, this is the full adder. I have 3 inputs here, and I want to add the 3 inputs together. And I have 2 outputs here. I have 2 outputs. So now, as you see here, I'm gonna put all possible cases here. Again, nothing is new, similar to what we did before. And then if you add 0 plus 0 plus 0, result is 0, and carry is 0. Same thing for the other one. 0 plus 0 plus 1, I have to get 1 and 0 here. If you add 1 plus 1 plus 1, I have to get here 1, and the carry is 1. If I, for example, another example, if you add 1 plus 1 plus 0, I'm gonna get 0, and then I have a carry here, and so on. Is that okay? And then what should you do next? So this is how it looks like. What you do next? I need to simplify this one, and then I have to simplify this one. That's it. So now I'm gonna use maps. So if I use maps this way, I'm gonna simplify this one, and then I'm gonna simplify this one. Yes.
On your previous slide, you said the full adder is a combinational circuit that adds 3 bits.
Input, 3 bits input.
And then it said, and then it's at the very end, it said it's called a half adder. You go back to the previous slide.
Which
You know, back forward.
yeah.
It was at the full adder definition. This one.
Yeah.
It's called a half adder.
No, it's called, I'm sorry, I'm gonna correct this one. This one is called full adder. I'm sorry. Half adder I already explained. Half adder is used if you want to add bit to it. Thanks. I'm gonna correct this one. Okay. So now I'm gonna do simplification as we did before. If you do the simplification, you are gonna get S this way, and you're gonna get C this way. Actually, if you see here, it's a really very rare case. Here, I can't do any simplification because I have to make 4 groups here. I can't make bigger groups. So this is some product is gonna give you the same thing. I can't combine groups. Anyway, so by this way, I can get summation and I can get carry. So what I'm gonna do right now, so yeah, you can implement it this way. You can implement this way for the sum. So this is actually similar to this one here. For carry, this is the carry, which is similar to this one here. Is that okay? Now, you understand what I'm doing? What I'm doing is I'm doing full adder. Full adder, it has 3 bits. It's gonna add the 3 bits. It's gonna produce sum and carry. Okay. And this should be the carry, and this should be the sum. Okay. So what I'm gonna do right now, I'm gonna do some algebra manipulation. I'm gonna do some trick. Okay. In order to prove to you or to show you that I can implement the same circuit using 2 half adders. So this is full adder. So full adder, so this is half adder. I'm gonna show you how. And this another one is actually half adder. So using 2 half adders, I can make full adder. And from here comes the name. Why they call it half and full? They call it half because actually for the full adder, it's gonna have, it should have 2 halves. Anyway, I'm gonna show you how. So how I'm gonna just do some little modification on this one, okay? So that this one is gonna be equivalent to XOR between X, Y, and Z. So this is the input is here. This is equivalent to XOR to X, Y, and Z. I'm gonna show you how. Why I'm doing it? Because I need it, and I wanna show you. I'm gonna do again. Don't be confused. You can implement it this way. It's totally fine. What I want to do, I want to implement it using 2 half adders. That's why I'm going to do a little bit more. It's not simplification because I already got the most simplified version from the key maps. Don't be confused. It's not simplification. It's just I'm gonna do some manipulation here so that I'm gonna get the same thing using XOR. Okay. So see how I did it. So what I did here, as you see here, number 1 for the summation. This is the one I got from the key map. This is the most simplified one, okay? But I just want to put it in XOR format or in a different format. So if you see here, I got X prime here common. If you see between these 2, X prime is common. And then here, I found X is common. I got it this way. So if you notice, what is this? So here, this one is X prime. And this is Y prime Z, Y Z prime. Do you remember this one? What this one is? Y prime Z, Y Z prime. This is XOR, right? So this one can go to XOR. Okay. This one also can be XOR. I'm not doing simplification. I'm just want to put in the format of XOR, but it's not simplification. I didn't simplify it. You got what I'm saying? Just from the format and or I'm gonna put it just in XOR as this. Okay, anyway. So if you notice here, so now, and this one here, so look what's gonna happen here. So here you have y XOR z, y XOR z here, okay? But this is the complement of it. So you have XOR and something, and you have X and something inverted. So it's like you have XY prime or Y prime X. So what this one is, it is another XOR. So there is another XOR between X and so you can, okay, if you are confused, I can consider this one as N. I can consider this one as N, okay? So, and there is a prime here. There is a prime here. So it's like X prime N or X N prime. So this is actually X XOR N. Okay, and this is N. You got what I'm saying? So I just did some manipulation so that I can get it in the format XOR. Why? Because I have other half XOR. So now, in order to get this S, and as I explained before, if you have X XOR Y XOR Z, so I have here, if you have here X XOR Y XOR Z, it's the same thing if you just do one XOR here and one XOR here. It's the same thing. You understand what I'm saying? It's equal. So same thing for AND and for OR, same thing. Anyway, for XOR, 3 XOR, so it can be, I can do 2, and the result can go to this one. And by this way, what I can do is, because this is half other, this is half other, and this is half other, okay? And we have XOR here, we have another XOR here. Is that okay? So what I can do here in order to get the summation is, look here, to get the summation is X here, Y here. So I'm gonna get X XOR Y, and then I'm gonna input Z here as well. Okay, in order to get X XOR Y, which give you S. Okay, so again, key map gives me this one. This one here, I did some manipulation to make it in this format, and then using this one, I can do it using the key, using the half others, because as you see here, we have X XOR Y is going to input here, and then I'm going to input here Z. So here I'm going to get S. Okay. Same thing for the carry. For the carry, look what I did here in the carry. This is for the carry. This is the carry is here. Okay. So again, I'm going to also do some manipulation here. Okay. So here I got Z common. Z is common here. And this one becomes XOR. I got here XY is common. So you can see here XY here is common. Okay. So this term is gone. So actually here's the carry. I can get it from this one here. Z X XOR Y or XY. Okay. So the way I'm going to do it here using the, as you see here, you have here, look here, I need this term here, XY. So XY actually is the carry of the first one. So this is, if you have here, if I input XY to the first half other, the output here XY. So I need to connect OR here, this OR. I need to connect OR here. And this OR is going to get XY, which is the carry of the first one, okay? And then it's going to get the carry of the second one. The carry of the second one is actually this term here. Okay, let me tell you the conclusion. The conclusion is full other, you are going to add 3 bits, and then you are going to get carry and sum. Okay, and already I have implemented it this way. I already done this way, and then I did some algebra manipulation. Okay, I just put it in the format that can help me to use half other to implement the full other. And the way I did it here, you can input X and Y to the first half other, and then connect the sum here to the input here. The carry here, I'm gonna take it to give me the final carry here, this way. Okay, and then the input here is gonna be Z. Okay, and then what you are gonna get here is sum and carry. if you OR these two carry together, you are gonna get the final carry. So using two other and one OR gate, I can make the full other. This is one way. The other way is you can use this one and use this one. Okay. Again, here XOR. How you made it? I'm gonna tell you how. Actually, the summation here is XOR. As I explained in half other, the summation is XOR. So you're gonna get here X XOR Y. And because the input here is Z, so here the summation is gonna XOR the inputs, which is Z XOR X XOR Y, which is exactly similar to this one. Is that okay? Let's look at the second one. The second one here, what do you need in the second one? Okay, what I need, you remember the carry. The carry is gonna end these two together. So the carry here is Z, and it was X XOR Y. This is how the half other works. The way half other works, the summation is XOR. The carry is end. This is how it works. Okay. And then if I get this one here and I get the carry here, which is XY, so I'm going to end up with this one. Any questions? With? Okay. I need volunteers. It's very easy quiz. I need some volunteers. I need some heroes. Volunteers. Go at the back. Yeah, you can start. Don't forget to write your name. Okay, take a look. So I give you a function, I give you don't care, and this function, the first part of the function is min terms. Okay, so these are the location of ones. I give you the don't care, also the locations of the don't care. And then in the first part, I ask you to simplify this function in sum of product form. And once you get this answer, I want you to validate it. Make sure what you get is correct. Okay.